This project is about creating an electric circuit with a photoresistor, which is a sensor that changes its internal resistance and therefore its voltage output based on the illumination level of the environment. The voltage generated by the photoresistor can be read by the Arduino and used for a particular purpose, such as turning a switch on-off, for example. The goal of this project is to capture the output voltage of the photoresistor and use that to turn an LED on if the illumination level is below a certain threshold. For this project, we are going to use the onboard LED on the Arduino board, which is wired into pin 13. So here we have the Arduino board and the solderless breadboard. We have one photoresistor on the breadboard. Power to the circuit is provided by the Arduino board itself. You can see here the red wire going into the 5-volt pin on the Arduino board. The wire goes into the same row on the board where one terminal of the photoresistor is located. The other terminal of the photoresistor is connected to a 330 ohm resistor. Ohm's law tells us that the current flowing into the circuit and back into the Arduino will be 5 volts divided by 330 ohms, which is about 15 milliamps. That should be good for turning on and off an LED, which is usually, which usually don't fare too well if the current is above 20 milliamps. Although it's very likely that the onboard LED is protected against higher currents. Anyway, the bottom terminal of the resistor is then connected back to the ground pin on the Arduino through this black wire. In order to capture the output voltage of the photoresistor, we need to add an extra wire, the green wire here. The green wire is connected to the bottom terminal of the photoresistor and to the analog pin 0, A0, on the Arduino board. Since the voltage generated by the photoresistor is an analog quantity that varies continuously over a range of values, we need to wire it to an analog pin and not a digital pin on the Arduino board. Before going over the software that controls the turning on and off of the onboard LED, let's do a demonstration to show that the circuit works as it is supposed to do. So the ambient light in this room is pretty low already, and therefore the onboard LED is going to be on the moment we plug the board into the computer. So the board is already plugged in. As you can see, the LED is on already. Now, to simulate a brighter environment, we use the flashlight of my cell phone and sweep it over the photoresistor, which I'm going to do now. You can see the LED will be turned off. Yeah, like that. Try again. So let's do it again. No flashlight, LED is on. With flashlight, LED is off. Good. Let's now describe how the software controlling the board is written. We define 3 variables: sensor pin, LED pin, and sensor value at global scope. The reason why they are a global scope is because they need to be accessible from both the setup and loop function. If we define these variables inside the setup function, say, they would not be accessible from the loop function. The variable sensor pin identifies the input pin for the photoresistor, in this case A0. That's the pin that collects the voltage from the photoresistor, so to speak, and so it must be declared as input, as you can see here in the setup function. The variable LED pin identifies the value on or off of the onboard LED, and therefore it is declared as output, as you can see here in the setup function. The variable sensor value captures the value generated by reading the analog voltage of the photoresistor. This is done in the loop function here. Now, if the value read is less than, say, 100, like in this case, remember that the output of the analog read function is between 0 and 255. It means that the ambient light is low, and then we turn on the onboard LED by writing high to pin 13, as we do here. Otherwise, we turn it off by writing low to the LED pin. Thank you.